Today we're going to introduce statistical tests to compare two populations. We will focus on comparing mean and variance, which are the problems we encounter most frequently. The tests we will consider are similar to those we introduced for single populations. We will also consider the Wilcoxon test, which is a non-parametric test. A particular case that requires attention is that of paired samples. In this case, it is possible to get more power in the test by taking advantage of the fact that the samples are correlated. In today's video, we're going to develop some statistical tools for two-sample problems. These are problems in which we want to compare samples coming from two populations, and we want usually to test whether the populations are the same or have the same characteristics. We start by comparing two population means. The usual test for comparing the means from two populations is the two-sample t-test. This comes about exactly as it did for the one-sample problem, only in that case we were comparing the results of the sample with one fixed value for the mean. In this case, we want to compare the means from two samples. So suppose we have two samples, x1 up to xn1 and y1 up to yn2. And assume that they come from normal distributions. The first sample from a normal distribution with parameters mu1 and sigma1 square, and the second sample from a normal distribution with mean mu2 and variance sigma2 square. We want to test the null hypothesis that these means are equal, that is, that mu1 is equal to mu2. Let x bar and y bar be the sample means for each sample, and sx squared and sy squared be the corresponding sample variances. Recall that the standard error for the sample mean is the standard deviation of the sampling distribution for the mean, given by sigma 1 over square root of n1 for the first population and sigma 2 over square root of n2 for the second. These are unknown values and are estimated by Si over square root of Ni for I equals 1 or 2. Si squared is the sample variance. The test statistic in this case is the difference between the sample means divided by the standard error of the difference of the means, which we denote SEDM. The standard error of the difference of the means is calculated by using the fact that for two independent random variables, the variance of their difference is the sum of the variances. Let's prove this. So assume that x and y are two random variables and denote by μx and μy their means. So the variance of x minus y is the expected value of x minus y minus μx minus μy, which is the mean of x minus y, and all squared. Now we can write this as x minus μx minus y minus μy. And then we square the whole difference. Now the square of this difference is the square of the first term, x minus μx squared, plus the square of the second term, which is y minus μy squared, minus twice the product of the first times the second, which is minus 2 x minus μx y minus μy. And now, since the expected value is linear, the expected value of this sum is the sum of the expected values. This term is the variance of x, this other term is the variance of y, and the last term is twice the expected value of the product of x minus μx times y minus μy. This expected value is known as the covariance between x and y, and it has appeared in a previous video. Now, if the variables are independent, the covariance is 0, and we get that the variance of the difference is equal to the sum of the variances. If we assume that the two variances are equal, which corresponds to the classical test, then the standard error can be calculated using a pooled estimator for the variance based on the standard deviations from the two groups. This test is implemented in R with the function t.test, as in the one sample case. The option bar.equal must be set to true in this case. Let's use this test on the data we had in the last video. Recall that we had two sets of data. The first one corresponded to fish, which had been fed different diets, and we wanted to compare the result of these diets. And in the second example, we had subjects that had gone through two different methods for improving reading comprehension, and the score was the result of a test on reading comprehension. And we also wanted to compare the results of the two methods. Okay, so now we want to load all the information for the dataset we used in the last video. So the first example is for the fish test, and we assume that they have equal variances. So we apply the t-test to the two populations with bar.equal set to true, and we have the result in the console down here. So it says that we have a two-sample t-test. The data sets are fish1 and fish2. The value for the test statistic is 0.378. The degrees of freedom is 68, and the p-value is 0.706. The alternative hypothesis is that the true difference in means is not equal to 0. We also get a confidence interval and sample estimates for the mean of x and the mean of y. So here we have a very large p-value. This means that there is no evidence in the samples to reject the null hypothesis that the two means are equal, which is the null hypothesis in this case. Another way of implementing this test using the function width is using as first argument for width the data frame that has the data that we want to use for the test, and then in t-test the argument is in the form of an equation in which we have the variable that we want to compare and the factor that determines the groups, which in this case is group. We carry the test with this command, and the result, of course, is exactly the same, although it has a slightly different shape in the outcome. Recall the second example where we had the improvement vectors for the two methods that we considered. So we have imp1 and imp2, and using them we carry out a test. And in this case, we get a p-value that it's almost 0. So in this case, there is very strong evidence that the two groups are different. Now let's look at the second case where we have unequal variances. The classical t-test requires equal variances, but there is an extension due to Welch to the case of unequal variances. In this situation, variances are estimated separately for each sample. The distribution for this statistic is not the t-distribution, but it may be approximated by a t-distribution with a number of degrees of freedom that is calculated from the sample standard deviations and the group sizes. This parameter is usually not an integer. And this is the default test when you use t.test. Let's carry out again the same tests, but now we will not assume that variances are equal. So first we carry out the test for the fish population, and we get also a very large p-value. It's very similar to what we got before, 0.706, while now it's 0.7323. For the other example on the reading comprehension, we get again a very small p-value, so we would reject the null hypothesis. We may also wish to compare variances from different samples. The test for this is known as Fisher's F-test, and it's based on the quotient between the two variances, with the condition that the bigger variance must be on top. The distribution for this quotient is known as Fisher's F-distribution and has two parameters that correspond to the degrees of freedom of the numerator and the denominator. Let's first calculate the variances for fish 1 and fish 2, and the result is clearly different. So in the previous test, we should have opted for the second option for unequal variances. And now we are going to calculate the quotient between the two variances. We have to put the variance for fish 1 on top, because the test requires that the bigger variance be in the numerator. So the F ratio, which is the test statistic in this case, is 4.71, and now we calculate the p-value associated to this test. Is about 10 to the minus 5, and this is a small value, so in this case we have evidence to reject that the two variances are equal. The test can be carried out with the command bar.test, as in here, and the argument are the two data sets that we consider. So we carry this test, and the result says that we are doing an F-test to compare two variances. The data come from fish 1 and fish 2. The value for the test statistic is 4.712, which is the same value we had before. We have 29 degrees of freedom for the numerator and 39 for the denominator, and the p-value is 10 to the minus 5. It's the same value we obtained with our calculations. The alternative hypothesis is that the true ratio of variances is not equal to 1. We also have a 95% confidence interval for the ratio of the two variances and a sample estimate for the ratio, which is the value for the F statistic. Let's do the same for the second example regarding the reading comprehension methods. And here the two variances are not so different as before. So if we apply the variance test, we get a p-value which is about 0.03719. So in this case, it would depend on the level of the test whether we reject or not the null hypothesis. If we choose a level of 1%, then there is not enough evidence in these samples to reject the null hypothesis of equal variances. If, on the other hand, we chose a 5% level, then since the p-value is less than 5%, we would reject the null hypothesis in that case. For the tests that we have just performed, we have assumed that the samples come from normal distributions. This may not be the case, but as we saw for the one-sample problems, if the sample size is large enough, then the central limit theorem says that the averages have an approximate Gaussian distribution. So if we have large samples, the procedures that we have described are valid, at least approximately. However, if we do not want to make any distributional assumption, we can opt for a non-parametric test, such as Wilcoxon's test. This test is useful when the assumption of normality is not justified. To calculate the test statistic W, we follow this procedure. We mix the two samples and then order them. We calculate the ranks for the elements of each group and sum the rank for one of the groups. We have now a combinatorial problem that consists of choosing n1 values from n1 plus n2 places. The test is implemented with the command wilcox.test. Let's carry out this test for the fish problem. The result says that we are running a Wilcoxon rank sum test with continuity correction. The data come from the sets fish1 and fish2. The test statistic is 561.5 and the p-value is 0.65. So as in the test we carried out before, the t-test, the p-value is large, so we would not have evidence to reject the null hypothesis. Observe that there is a warning message that says that it cannot compute the exact p-value when there are ties. Let's use this test for the other problem that we have. The p-value is almost zero. So in this case, we have strong evidence to reject the null hypothesis that the means are equal. In the second example that we considered in the previous video, we had results for a reading test before and after the subjects go through a reading comprehension improvement method. So let's now focus on one of the groups, say group 2, and we would like to know if the treatment had some effect on the outcome. Treatment in this case is the method, and the outcome is reading comprehension as measured by the test that the subjects followed. This is an example of paired data. We have scores before and after treatment for the same subjects. In this case, the two samples are clearly not independent. The score after treatment will be related to the score before treatment because it corresponds to the same subject. We may have an important correlation in this case that should be taken into account. Analyzing this data as if the samples were independent could lead to severe errors. Now remember that a while ago we showed that the variance of the difference is equal to the sum of the variances minus twice the covariance between x and y. If the covariance between x and y is positive, this equation says that the variance of the difference will be smaller than the sum of the individual variances. And this is an advantage because we have less dispersion and it makes it easier to detect significant differences between the means. In R, the same t.test function with the option paired set to true will do the test for paired data. So let's carry out this test for the data in the second example. To see the difference between the usual test and the paired test, we carry out first the test without assuming that the data is paired, and here is the result. We are carrying a two-sample t-test. The data come from group 2 pre and group 2 post. This is the test statistic, the number of degrees of freedom, and the p-value. The p-value is small, but not too small, so depending on where we set the level for the test, we would reject or not the null hypothesis. So let's carry out again the test, but now selecting the option paired equals true. So in this case, we are carrying out a paired t-test. The data are the same, and we have the value for the statistic, the number of degrees of freedom, and the p-value. The p-value is similar to what we had before in this case. It's a bit smaller, but not significantly smaller. Let's look at the correlation in this case, and we see that the correlation is really small. It's less than 5%. So the fact that the correlation is close to zero means that the two tests are almost equal. And in fact, if we plot a graph for the two scores before and after, we see that there is not too much correlation between these two variables. Let's carry out again the same test, but now for the other group in the same example. So now it's group 1. In this case, we have a very small p-value, but this is the test without assuming that the data is paired. So here the difference is very clear. If we carry out the paired test, we get a similar p-value. So in both cases, the tests are saying that we should reject the null hypothesis that the means are equal. So the scores before and after are different. Let's calculate the correlation, and we get a slightly bigger correlation in this case. And if we plot the two variables, we see also there is not a very strong correlation in these two variables. Let's look at a more extreme example. This is a classical example that comes from the book by Box, Hunter and Hunter, Statistics for Experimenters. It's a book on design of experiments. In this experiment, two types of material for shoe soles are compared, A and B, and these were randomly assigned to the left and right shoes of 10 boys, so that each boy had one sole with each material. To have access to this data set, we have to load library mass, and then here's the data set. So we have A and B. We start by doing a classical t-test, assuming that variances are equal, and in this case the p-value is large. It's bigger than 0.7, so it says that there is not enough evidence to reject the null hypothesis. Let's skip the hypothesis of equal variances, and the p-value remains more or less the same. But we have not used so far the fact that these are paired data. So let's now use the t-test with the option paired equals true, and we get now a p-value which is less than 1%. The change in this case has been important. We have gone from a value of 0.71 to a value of 0.008. And the reason for this is that if we calculate the correlation, we get a value which is very close to 1. So in this case, the variance for the difference will be much smaller than the sum of the variances. If we plot the data for this experiment, we see that there is a very strong correlation between the two variables. There is also a non-parametric test for paired samples, which is the one-sample Wilcoxon sign rank test applied to the differences. Let's do this for the shoes data. Wilcoxon sign rank test with continuity correction. The data are A and B, which are the variables for the shoes data set. And we have here a p-value of 0.01431. So in this case, there is a loss of power by using a non-parametric test. The p-value is considerably larger than what we obtain using the paired t-test. Today we reviewed the problem of comparing two populations. We focus mainly on comparing means and consider parametric and non-parametric tests. We also studied the particular case of paired tests, in which it is possible to take advantage of the existing dependence between the samples to improve the power. In our next video, we will go through an example in detail using R to calculate the test statistic and the corresponding p-value. We will also introduce functions in R that do all the process automatically and print an ANOVA table as a final output.